Hello, math nerds. It's Math 0028, Section 4.3 with Susan Wessner. I know you're all so excited. All right, so today we are looking at how to multiply, add, and subtract radical expressions. So once again, it's radical, dude. This is our last section of radicals, so we are so excited about that. First, we're going to look at multiplying radical expressions, and then we're going to look at adding and subtracting radical expressions. And what's going to be important is the order that you do them in, because the order that you do those two operations in, multiplying versus adding, subtracting, is totally opposite, so you got to be careful. All right, so let me get my pen because I always forget to do that. And off we go. All right, so we're going to recall from section 4.1 the multiplication property of radicals, which says if you have it as a square root underneath, like a product underneath the square root, you can split it into the square root of a and the square root of b. Now, I have not been splitting it up like that. We've been just underlining our perfect squares and then taking those square roots. So that to me just seemed a little bit easier. We were still using that property, but we weren't splitting it up so much. Okay, so when you are looking at multiplying radicals, what you have to do is, first of all, you're going to multiply the radicands. Remember, that's the expression under the radical first, and then simplify. So that's going to be very important that you multiply first. Very important, okay? And then simplify, step 2, okay? So like if you look at this example up here, we multiplied 2 times 18. That's where we got the square root of 36. It's still under the radical because all you did was just multiply the numbers underneath. And then you simplify. The square root of 36 is just 6. So that's what we're going to be doing, is multiplying first and then simplifying. All right. So on this first problem, we have the square root of 3 times the square root of 12. Well, you're going to go ahead and multiply those radicands. So 3 times 12 is 36, and then the square root of 36 is just 6. And no, they're not all that easy, but at least we start you off with a nice one, right? Okay, letter B. Now we have numbers and variables. So remember, you're going to multiply the coefficients, and we're back from chapter 3, when you multiply, you add your exponents. So we're going to add the exponents. So 32, we have the square root of 32, a squared b to the 5th, times the square root of 2ab to the 7th. So first I'm going to multiply 32 times 2, that's 64. This is still all under the radical, okay, still under the square root sign. A squared times a, remember add, that's going to be a to the 3rd because there's a 1 on that little a. And b to the 5th and b to the 7th is going to give me b to the 12th. Okay, so we've multiplied. Next step is to simplify. So, sorry about that. All right, so two of our terms under here are perfect squares, the 64 and the b to the 12th. We're not going to mess with them yet, because we still need to deal with the a to the 3rd. So for right now, in your next step, bring down the 64. Don't mess with it yet. You can go ahead and underline it because that's a perfect square. But remember, when it's an odd exponent, you have to drop back 1. So we're going to rewrite a to the 3rd as a squared and a to the 1st. b to the 12th is a perfect square, so just bring that down. Okay, so now go back and we're going to finish underlining our perfect squares. A squared is a perfect square, and so is b to the 12th. Now in the next step, we're going to take our square roots all at the same time. So start with the 64. The square root of 64 is 8. That comes outside. 64 is gone. A squared, if we divide that by 2, comes out as just a. The a squared is gone. Then jump over to b to the 12th, divide that by 2. That comes out as b to the 6th. And b to the 12th is gone. And the only thing left inside the radical is just the square root of a. And there's your answer. So really, after the first step, it's back to what we did in section 4.1. It is just simplifying radicals. That's basically all there is to it. Okay? Okay, so, oh, look at these big numbers. Good thing I have my calculator handy. All right, so we have the square root of 18, x to the 7th, y to the 4th, times the square root of 48, x to the 9th, and y to the 5th. Okay, so the first thing we're going to do is we're going to multiply those monster numbers. 18 times 48 is 864, which is disgusting. Okay, now add your exponents. On the x, 7 and 9 is going to give me 16, and on the y's, 4 plus 5 would be y to the 9th. Okay, now I'm going to try, 864 is not a perfect square. That would have been just way too easy. So let me tell you how I figure out the perfect square, the biggest perfect square that goes into 864. This is my thinking. I know that we want to multiply the 18 times 48 first, but think about what's the biggest perfect square that goes into 18. That would be 9, okay? Because think about your perfect squares over here, 9, 16, 25, 30, oh, that's a 3, 36, let me just scribble that out because I don't know how to erase, and 49. Okay, so in 18, 9 is my biggest perfect square. And then for 48, my biggest perfect square is 16. So now multiply those two perfect squares together. 9 times 16 is 144. So that's probably the biggest perfect square that goes into 864. But at least that's where we're going to start. So what I'm going to do now is I'm going to take 864, divide it by 144. So this is the thought process you want to go through so that you can figure out these perfect squares, okay? All right, that goes 6 times. That's going to be good. So we're going to rewrite 144 times 6 is what 864 is going to break down into, okay? So remember, what I did again was I looked at just the 18. The biggest perfect square that goes into 18 is 9. That's where I got the 9. The biggest perfect square that goes into 48 is 16. Then I multiplied those together because the 18 times 48 gets multiplied together. That's where I got the 144. That's a perfect square. So see if it goes into 864, which it better, and it turned out it went 6 times. So there's my big perfect square, 144, okay? Because looking at 864, I have no clue, okay? That's how I kind of figured it out. Now, the next ones with the variables, x to the 16th is even, so we leave that alone. Y to the 9th is odd, so I have to drop back 1 to y to the 8th and y to the 1st, okay? So now underline your perfect squares. We have 144, x to the 16th and y to the 8th. So I'm going to bring those square roots of those out front. So the square root of 144 is 12. That comes out front. The 144 is gone. Divide x to the 16th by 2. We get x to the 8th out front. Okay. Y to the 8th divided by 2 is y to the 4th out front. Okay, and that's going to leave 6y on the inside. So yes, the numbers when you're multiplying are going to be big, but if you think about the strategy that I used on this one, it'll help you figure out what the biggest perfect square is. That'll help you. Okay, letter D. At least the numbers are a little bit smaller. So we have the square root of 6a to the 3rd b squared c times the square root of 24a to the 5th and bc. So first thing we're going to do is multiply 6 times 24, which I don't know what that is. 144. Oh, how nice. A perfect square. The gods are smiling. Okay, now add the exponents. We're going to have a to the 8th because we have 3 and 5. On the b, I've got b squared and b to the 1st, so that's going to be b to the 3rd. And c is going to be c squared. All right, so we already have some perfect squares here. The 144 is a perfect square. A to the 8th is a perfect square. But b to the 3rd is not. We need to rewrite that b. Okay, so keep the a, leave that alone, and we're going to multiply it by b squared, drop back 1, and b to the 1st. C squared is a perfect square. Leave it alone. Okay, so make sure that you don't do anything with that yet. Now, underline your perfect squares. 144, a to the 8th, b squared, and c squared. Okay, and now we take the square roots. So the square root of 144 is 12. That comes out front. Okay, a to the 8th, if you divide that by 2, comes out as a to the 4th. That's gone. B squared, if you divide by 2, comes out as just b. So b squared is gone. C squared, same thing. Divide by 2 comes out as C, and the C squared on the inside is gone. So the only thing left on the inside is just B, the square root of B. So we have 12a to the 4th BC times the square root of B. All right. Okay, so hopefully you got that, because that was multiplying. Now, when we are adding and subtracting radical expressions, we're going to do the exact opposite. For these, you have to have what's called like radicals. And like radicals have to have the same index, which I always call the root, the same root, and the same radicand. Okay, so in other words, they all have to be square roots, or next semester they would all have to be cube roots or whatever. They all have to be square roots, and they have to have the same radicand. The expression underneath has to be exactly the same for you to be able to add and subtract them. So it's very similar to like terms. Like you can only add an x and an x squared with an x squared. Here you can only add a square root of x with another square root of x, things like that. Square root of 5 with another square root of 5. Okay, so if you look at some examples here, this first set of pair of radicals are like radicals. 2x to the square root of 6 and 5x times the square root of 6. They both have square root of 6 on them, and the terms outside are the same also. 2x and 5x are like terms. Now, down here we have negative 4 and the cube root of 17y, and 1/2 times the cube root of 17y. So the radicals are the same. Now the coefficients out front are very different. You've got a negative and a fraction, but they're still like radicals because the radical part is the same. So it'd be like if you had negative 4x and 1/2 x. They're like terms. They're not exactly nice like terms, but they're like terms. Okay? So these on this side are not like radicals. We have 9 times the square root of 3 and 9 times the cube root of 3. So because the roots are different, this is a square root, okay, that 2 is understood to be there, but we don't write it. Those are different, so that's why they're not the same, not like radicals. And here, 8ab times the square root of 5 and AB times the square root of 10, the radicands are different, so those are not like radicals. So it has to be the same root and the same radicand for you to be able to add or subtract the terms. Okay? All right, so this page is crazy. We are not going to go through this whole distributive property to add our radicals. We're going to keep it a lot simpler. Like this middle step in between the 5 plus 3 times the square root of 2, we're not doing that. Okay, look at this problem. 5 square root of 2 plus 3 square root of 2. Those are like radicals because they both have the square root of 2. So if you have 5 of them plus 3 of them, you have 8 of them, 8 square root of 2. Okay, so technically you're using the distributive property. We're just not going to write it out because it's a pain in the butt, and also it kind of confuses people. So look at this example down here. 2 square root of 3 plus 4 square root of 2. You can't do anything on that because the square root of 3 and the square root of 2 are not like radicals. So that would be simplified as much as possible. Okay, so here's our procedure for adding and subtracting radicals. And it's going to be the opposite of what we just did with multiplying. With multiplying, we had to multiply first, then simplify. Here, with adding and subtracting, we're going to simplify first. Very important, simplify first. And then add or subtract, okay, if you have like radicals. So that's a big difference there as far as the order of what you're doing everything, okay? So I know that when this was written, these were meant to be done further on in the section, but we're going to go ahead and do them now. A is not too bad. B is kind of a pain in the butt, and they meant to put that further along, but we'll do it now anyway. All right, so look at A. We have 5 square root of 2 minus 3 square root of 2 plus 12 square root of 2. So those are all like radicals because they all have the square root of 2. They're all like radicals. So you're just combining the coefficients out front. So 5 minus 3 is 2 plus 12 would be 14 square root of 2. And that's your answer. Okay, so that one's not too bad because it's basically just like combining like terms. Now, letter B, and this is what we'll get into a little bit further on in the section, but they stuck it right here at the beginning. These are not like radicals. We have 3 square root of 12 minus 5 square root of 27. So the steps we just talked about, you have to simplify first and then see if you have like radicals. So what you're going to do is 12 is not a perfect square. So I need to write down my perfect squares over here, 16, 25, 36. That's as far as I need to go because 27 is our biggest number. So 12 is right here between 9 and 16. I'm going to bring down the 3 that's on the outside. Okay. And the perfect square that will go into 12 is 4. So 4 times 3 is how we're going to rewrite that 12. Okay, that's the first term. We bring down minus 5, and now we need to break down the 27. Well, 27 is here between 25 and 36. So go up. 25 doesn't go. 16 doesn't go. 9 goes into 27. So we're going to break 27 down into 9 times 3. Remember, that first number has to be your perfect square. So now underline your perfect squares under your radicals. We've got 4 and 9. Okay, so on the first radical here, the 3 is already outside, so anything we bring out, it's multiplication. The square root of 4 is going to come out as 2. That 4 is gone, so we're left with the square root of 3 on the inside. And then we go over to the next term. We have minus 5. Now, whatever we bring out is multiplication. Take the square root of 9. That would be 3 comes out. The 9 is gone, and we're left with square root of 3. Okay? So now you need to multiply your coefficients out front. 3 times 2 is 6, square root of 3. And then minus 5 times 3 is 15, square root of 3. So now we can subtract them. Okay, so here's the thing. The adding and subtracting part of the problem is the easiest part of the whole stupid thing. It's getting to the point where you can add or subtract that's a pain. Okay, so that's where you have to do all the simplifying. So we have like radicals, square root of 3's. 6 minus 15 would be negative 9, square root of 3. And that's your answer. Okay. All right. So now we go back to simpler ones. I think because she meant to start us here, but that's okay. All right. So we have letter A is 3 square root of 2 plus square root of 2 plus square root of 2. So those are all like radicals because they're all square root of 2. Okay. And so what we're going to do is add them up. Now what you need to remember is that there's understood to be a 1 in front of each one of those square roots of 2. So you have 3 plus 1 is 4 plus 1 would be 5 square root of 2. And that would be your answer. Okay. Look at letter B. Here we have negative 3 square root of 7 plus 2 square root of 7. Once again, those are like radicals. They're both square root of 7. So you combine your coefficients. Negative 3 plus 2 would be negative 1 square root of 7 because you subtract there. Okay. Now remember, WebAssign does not like those 1s as coefficients. So when you put it into the homework, you would just put the negative square root of 7. Don't put that 1 in front. Okay. All right. Letter C. We have negative 3 square root of 11 minus 8 square root of 11. Okay, so again, we both have like radicals there, square root of 11. So we combine the coefficients out front, negative 3 and negative 8. You would add and get negative 11 square root of 11. And that would be your answer there. Okay. Letter D. We have 2y square root of 3 minus 9y square root of 3. So you have to check two things. First of all, are the radicals the same? Yes, they're both square roots of 3. You also need to check that you have like terms outside. 2y and 9y, yes. If it was a 2y and a 9x, you couldn't do anything, okay? But since those are like terms out front, you can now combine those. So 2 minus 9 is going to be negative 7y and the square root of 3. So notice on all these, the radical part does not change. It's just like combining like terms. The variable part, it's got to stay like it started. So that square root of 3, like it started, stays the square root of 3. Okay? All right, so now we get to the ones where it's a little bit more involved. Okay, so we have the square root of 45. plus the square root of 125. Now, those are not like radicals, and they are not perfect squares. So I'm going to write down the perfect squares over here on the right-hand side: 9, 16, 25, 36, 49, 64, 81, 100, 121, and 144. Okay, so the first one, 45, is right here between 36 and 49. So if you go up, the perfect square that's going to go into 45 is going to be 9. Okay, so just keep your calculator handy so you can check this stuff out. So it'd be 9 times 5. Okay, now plus we need to break down 125. Well, 125 is here between 121 and 144 on our list of perfect squares. So we go up, and the number that's going to go into 125 is going to be way up at 25. So that's going to be 25 times 5. Okay, so you need to make sure you break those down. That's the first step. Now, underline your perfect squares. The 9 and the 25 are the perfect squares. Okay? In the next step, I'm going to take the square roots of those perfect squares. So the square root of 9 is 3. That comes out front. I seem to have lost my pen. Just a sec. Oops, what's up here? I'm having some issues. Please stand by. Technical issues. I don't know what's going on. Oh, this computer has worked great up until this point. Let me see if maybe I unplug something. Let's see if I can get it back. Oh, poop. Let me see. Now we have nothing. Oh, now we got something to work, maybe. Let's see if we can get it back. Ah, ta-da! I'm so excited because I didn't want to have to do this video again. All right, so I think I pushed on something I wasn't supposed to. All right, so the square root of 9 is 3. That comes outside, and we're left with the square root of 5 on the inside. Okay, plus over here we have the square root of 25 comes out as 5. 25 is gone, and we're left with the square root of 5. Okay, so now we do have like radicals. They're both square roots of 5. So 3 square root of 5 plus 5 square root of 5 would be 8 square root of 5, just like that. Okay? All right, letter F. That's a big number, 128. We have 4 square root of 128 minus 3 square root of 32. All right, so 128 is down here between 121 and 124. And to tell you the truth, I don't even know what perfect square goes into that. Let's see. I'm going to try 64. Oh, it works. Okay, so as you go up, if you divide by 121, no. 100, no. 81, no. 64 goes into 128. Okay, so you just have to use your calculator. That's what I just did. So you're going to rewrite it as 64 times 2. Okay, bring down minus 3. And then 32 is right here between 25 and 36. If we go up from there, 16 goes into 32 2 times. 16 times 2. Okay? So, underline your perfect squares. We have 64 and 16. So the square root, we're going to bring those out now. So keep the 4 on the outside. The square root of 64 comes out as 8. The 64 is gone. And we have square root of 2. Then minus, bring down the 3. The square root of 16 comes out as 4. The 16's gone, and we have the square root of 2. So now you need to multiply the stuff, the terms outside. 4 times 8 is 32 square root of 2 minus 3 times 4 would be 12 square root of 2. Okay? And now you've got like radicals, so we can subtract. So 32 minus 12 just gives you 20 square root of 2. And there's your answer. All right. Sorry about that delay back there a second ago. Hopefully everything's going to work now. Okay, I think we've got just a couple more. We have letter G is 3 times the square root of 3x squared minus 5 times the square root of 27x squared. Okay, so on the first radical, keep the 3. Now, the 3 under the radical, we can't do anything with that. But x squared is a perfect square. So I'm going to just underline it so that you remember that, because we're going to underline it again in a minute. So we're not going to take the square root yet. We're going to do that all in one step. But that is a perfect square, so we're good to go on the first term, okay? Then minus 5. Now we need to break down 27. So we have 1, 4, 9, 16, 25, 36. So 27 is here between 25 and 36. And if you go up, the perfect square that goes into 27 is going to be 9 times 3, and we have x squared still under the radical. All right. So now we want to underline our perfect squares. Okay, so we underline the x squared in the first radical, and in the second radical we have the 9 and the x squared in the second one. Okay, so on the first radical the 3 is already outside, that stays there, but the x squared, if you divide that by 2, comes out as just x, so x squared underneath is gone, and we're just left with the square root of 3. Go over to the second radical, we bring down minus 5. Now the square root of 9 comes out as 3, so the 9 is gone, and then the square root of x squared, divide that by 2, comes out as just x, and the x squared is gone. So we're just left with square root of 3, okay, under the radical. So we have 3x square root of 3, it's our first term, and then multiply here, 5 times 3 would be minus 15x square root of 3. Okay, so now we have like radicals, both square root of 3, and we have like terms outside. 3x minus 15x would be negative 12x and the square root of 3, and that would be your answer. All right, letter H. So here we have b squared times the square root of a to the 5th b plus 3a squared times the square root of a b to the 5th. That's a mouthful. All right, so the b squared that's on the outside, this is a common mistake people make. They say, well, can't we simplify that? No, it's not under the radical. So you don't take the square root of b squared that's on the outside. It's outside. You don't mess with it, okay? But we need to break down that a to the 5th because it's not even. So I'm going to drop back 1, a to the 4th, and a to the 1st, and then just the b. I'm going to write it to the 1st just so I remember, okay? But we'll get rid of that later. Now on the second radical we have plus 3a squared, that's outside so don't mess with it, and then I have a to the 1st. Now b to the 5th I need to drop back 1, b to the 4th, and b to the 1st. Okay, so now go through and underline your perfect squares under your radical. So we have a to the 4th in the first radical, and in the second radical we have b to the 4th. All right. So anything that comes out on this first radical is going to get multiplied by the b squared. So it's going to be b squared times whatever we bring out. Well, the only perfect square we have here is a to the 4th. So if I take the square root of a to the 4th, that comes out as a squared. And a to the 4th is gone. And what I have left on the inside is just a and b. All right? Now, come over to the second term. 3a squared comes down on the outside, okay, and we're going to multiply it. Now we're going to take the square root of b to the 4th, which when you divide it by 2 comes out as b squared, and that b to the 4th is gone. So now you're left with a b under the radical. Okay, so on the first term we have b squared a squared. I'm going to rewrite that as a squared b squared just because I'm a little OCD about that, and I like it to be in alphabetical order. So a squared b squared times the square root of ab, plus over here we have 3a squared b squared, just write it all together because it's multiplication, and the square root of ab. So now we have like radicals, the square root of ab, We also have like terms outside, a squared, b squared. Remember, the coefficient on this first term is a 1. So 1 plus 3 is going to give me 4a squared, b squared, and the square root of ab. And that is your answer. So I'm pretty sure that's the end of 4.3. The rest of it is you tries, which is in a separate video. So good luck with the homework and quiz.